Let's take a look at example 4.1.2, spring constant of a fixed beam. So in this example problem here, what they're asking us to do is to derive the spring constant expression. So we're looking for a K expression here of a fixed end beam of some length that they tell us is L. So the length of this beam is L. Thickness of the beam they give us as H. And the width here they give us as W. So we're doing this all in terms of variables. And they're telling us also to assume, and we can see this from the diagram as well, that the force F and the deflection X are at the center of the beam. So that's going to simplify our solution and where we pull our general equations from. So now that we've had the opportunity to read through the problem statement, understand what they've given us in the problem, what they're asking us to solve for, the next step is going to be to create our setup page. So in our setup page here, one thing that we realize is we're solving this in terms of given variables. So we don't have any numeric values for anything. We're going to solve it in terms of the variables they gave us in the problem statement and initial diagrams. So write my heading down on the top of the paper here, ME111, example problem 4.1.2. This is a spring constant of a fixed beam. So we should have down here a given diagram. Here's our fixed beam, total length they gave us is L, force applied at the center of F here. Here's my displacement X at the center of the beam. Then we look at a cross section of the beam over here in 3D. We have our width here and our thickness given there as H. So we have this all in terms of variables. I clearly write those out. L is my total length, H is my thickness, W is my width, and F is the force at the center of the beam, and X is my deflection right here at the center of the beam as well. What are they asking us to solve for? Well, they want us to solve for a spring constant expression. So we're looking for our K expression here. And the assumptions that we're going to make, which you've already given up above, but I like to rewrite my assumptions here. F and X are taken at the center of our beam. So our F and our X are right here at the center of the beam. So as we begin the solution to this problem, you can reference back to that setup page, see what they've given us within the problem statement and the given diagrams, what they're asking us to solve for, any assumptions we make as we start going through this. Now this is a relatively straightforward, simple problem, but one of the reasons I want to go through this is as we advance in our courses for mechanical engineering, we're going to notice that we're expected to be able to draw back on previous courses and go to other textbooks to reference various equations, tables, things that we've learned along the way. So they're not always going to teach every single thing, every single equation, variable setup. They're expecting that we've learned it from previous courses, such as mechanics of materials in this case here, dynamics, statics, things of that, and bring those back in. Know where to reference back to get those key equations. So specifically here, we need to reference back to our mechanics of material course here and take a look at the force deflection of a fixed beam. Now for that, we can go back there and we can find this relationship here. Our X is equal to L cubed over 192 times E, modular elasticity, times I sub A, where this I sub A is our area moment of inertia, times F here, our applied force. Now, one thing to think about as we're referencing back to old textbooks or we're just going on the internet, wherever we'd be going to get these general equations, really pay attention to what variables they're using and how they relate to the variables that this text or this problem that we're doing uses, and what is the correlation between those two. Sometimes there may be discrepancy. They may use S in one and X in another. We don't want to confuse these, so make sure we understand, look at the diagrams when we reference back these equations and make sure, okay, I understand L is this, I is this, A is this, whatever it is. So that's why I always like to write it down here and reference it back to the variables we're using. Or maybe if it wasn't quite on, I'd change this right here and spell it out for the variables we're using for our problems. This is one of the main reasons I wanted to go through this, was to stress that point there. So in our case, X is the deflection at the middle of the beam. So there's our deflection at the middle of the beam right there. F is the applied force at the middle of the beam. There's our F there. And our I sub A is the moment of inertia about the beam's longitudinal axis. And L is our total length of the beam. So from that there, we need to figure out, okay, that's great. I have my L. Now I need to figure out what is my E, what is my IA, how do I plug those in now in order to search for my X here? Well, the first thing we can do is we can go to our general equation for area moment of inertia. We see have the integral of r squared dA But specifically, again, if we're referencing back to R, so there's a table that we can go to get our IA here for this here. So from our specific beam, we have a rectangular cross-section. We know the width, we know the thickness given to us in variables within the problem statement. So therefore, we can use our area moment inertia equation here of W times H cubed, or width times our thickness cubed, divided by 12. And again, just in case, doesn't relate back exactly as the variables we're using, I write those out. W is my beam thickness, W is my beam width, H is the thickness of the beam. So we can reference back to any of our mechanics materials, textbooks, or anything where we have a chart showing us the various deflections for configurations of different beams. So this one in particular, we have a beam fixed at both ends, not just a load support at both ends, but fixed at both ends, and make sure we're looking that up. And we have a concentrated center load. So we can go back to old textbooks, we can look on the internet, any type of reliable reference that we can get these equations from. So this is where we pull up the equation here that we saw before, for if we're looking for our max deflection, our change in deflection there at the center of this beam here. So there's our center load there, dead centered L over 2 there. What we end up with is P, which is our load, in our case this is an F there, times L cubed, where L is that total length. So we have a capital L in our particular case there, over 192 EI. So this is where I mentioned, yes, it's very, very similar to the variables that we're using in our problem, but not exact. So like I said, we have a capital L there and an F here that we're using. So when we look at this equation here, and we got to plug it back into ours, we make sure we swap out the lowercase l for the capital L and the capital P for our F as we plug those in. But this is where we get that relationship for the max deflection at the center of the beam for a fixed beam at both ends with a concentrated center load. So if we wanted to find our expression for our inertia I sub A, for our area moments of inertia for a common geometric shape, in our case here we're dealing with a rectangular shape here for our beam, again we can reference back to our mechanics of materials textbook. We look back here and we see, okay, here's a rectangular shape. I really wanted about our x-axis right here at the center. So I see, okay, this is what I'm looking for here. So my equation here is 1/12 BH cubed. So that's our expression. If we reference back to ours, we weren't using B and H in here. Our B was really our width W, and our thickness here, we were still calling H there. So our B becomes W, our H remains the same, and it's about our center point here for our beam. So again, there's our equation right there. We can plug that back in and swap out our B for a W, and this is now I sub A. So the next thing that we want to do is plug back in to our force deflection equation that we had before. So I'm going to rewrite out our force deflection equation here. X is equal to L cubed over 192 E times IDA, which now for our area moment of inertia here, we have this relationship that we looked up here, WH cubed over 12. So I can plug that back into this general equation here, rearrange, and what I end up with now is my X is equal to L cubed divided by 192E times this new relationship here for IA, WH cubed over 12 times F. I can rearrange this, simplify this down, put my 12 up top. My 12 up my top is going to cancel with part of this 192 on the bottom. Reduce and simplify. I find out that X is equal to L cubed over 16 times EW times H cubed times my F here. So now what I'm going to do here is I am going to rearrange and solve for F. So when I do that there, I'm basically flipping this over. So F is equal to 16E WH cubed over L cubed times my value for X. Now the reason I want to do this is because the spring constant is the ratio from Hooke's law, F equals KX. We have that there, and we can rearrange Hooke's law in order to get the force from the resulting deflection here. So K is equal to F over X. And remember, this is what we're looking for in our problem statement, is an expression for our spring constant K here. So we can rearrange that. K is equal to F over X. So I can take this here and now put that x over here. So f over x is equal to exactly this here that I solved for. So I do that there. K is equal to f over x is equal to 16e times wh cubed, width, thickness, length, all over my L cubed there. So I can solve this now, plug that right in. K is given by this expression here, 16e times wh cubed over L cubed. So there's my final answer for my expression for my K value there. So now that we've done this the longhand way, where maybe we didn't know this was readily available to us, or maybe we weren't sure how accurate a chart like this was, didn't have it in our textbook, so we went back, referenced our old mechanics of material textbook, went through, found a beam that's fixed at both ends with a concentrated load at the center, where we could get an expression for our max deflection at the center of that beam based upon that center load, and went from there and derived our equation for K. Well, we could have referenced back to table 4.11 here, our spring constants for common elements, and noticed if we go down just right and found it, there's our fixed end beam right there. There's our length L, there's our center load right there. There is the profile with our width and our thickness there, and it gives us that K value right there if K is equal to 16e times WH cubed over L cubed there. So we could have gone right to this chart from the beginning, just based off of what they gave us in the problem, and that was our final answer right there. So again, maybe we didn't have this chart available to us, maybe we didn't know where to look in our book, or maybe we wanted to double check. So both ways gave us the same solution at the end for our expression for K. One, we could have just gone right to a table, picked it off, and there it is. The other way, we went through and did it the longhand way and kind of proved to ourselves where it came from and understood the relationship for this equation.